Can any one of you please confirm that you can see the presentation and also hear me clearly? Please confirm.
Yes, sir.
Okay, so you can all hear me as well as see the presentation. Okay, uh, right. So before I start the technical discussion, of which the presentation is right there before you, I should first like to have a discussion on the broad terms of this course, Introductory Computational Physics. This is the first of the four core courses that you are to take as a part of your computational science minor. So those who are taking this course will take over and above their regular ICT load, shall have to take a minor and an honors in computational science. And as such, you shall have to study four core courses. The first one is this, Introductory Computational Physics. Then in the next semester, that is autumn 2022, this will be followed by computational and numerical methods. And next year, winter, you shall have to do two more courses, high performance computing and modeling and simulation. So this is the first of those four courses. This is based on physics. Basically, you shall be learning some science over and above your ICT engineering curriculum. So that is something that will give you some extra value as a student, maybe even also as a professional later, or maybe even an academician later. So first, therefore, we shall take up the issue of what are the things that are expected of you, or you should also expect out of this course. This course is computational physics. Computational as in, you shall have to make use of your knowledge of computational programming. You have already done some coding, learned some coding languages, algorithmic design, those techniques. You shall be using that. Mostly the kind of coding that you have done, I believe, are geared towards solving some engineering problem or practical industrial level problem. Now the kind of coding that you shall have to do as a part of this course will be designed towards learning or solving some physical problem, right? Um, by the way, those who are familiar with my methods, please just we will know, and those who are not, some of you are attending my classes for the first time. Some of you did that last semester as a part of the electromagnetic theory course. Please just keep a watch on the recording tab, the red recording tab at the top left. Occasionally there can be issues. And I also hope that you are able to hear me clearly, because in my previous class with another senior batch of yours, there was some issues with the recording. Sorry, I mean the sound quality. So can you just please once more confirm that you can hear me with full clarity? Hello? Can one
Yes,
of...
sir. Yes, sir.
Okay, okay. Thank you very much. And you can also see the presentation, but I'm not talking about the presentation right now. I'm talking about some broad terms of this course. So as I was saying, so basically you shall be using your knowledge of programming. You shall be applying your programming skills to solve physical problems. Now, as a part of this course, the stress that I shall give will be on the physics aspect of it. I do believe that you are well aware of coding techniques. So coding techniques are not things that I shall be teaching you. I mean, I shall not be teaching you any programming. I shall be teaching you how to design the basic algorithm of certain physical problems, certain mathematical methods that you shall be applying on certain physical problems. So that is the basic purpose. And this course will be broadly divided into three categories. The course material. Course material will be divided into three broad categories. One will be mathematical methods. That is important. So once you know those mathematical methods, then you can apply those mathematical methods in your coding. So you can make use of those mathematical ideas to design codes, programs. Um, so as I said, the basic content of the course, one aspect, there are three broad areas content-wise in this course. One will be mathematical methods, as I mentioned. The second will be basic physical concepts, such as the slide, such as contained in the slide that is right there before you. So basic physical concepts, which applies to all domains of physics. So be like, Newton's mechanics, Maxwell's electromagnetic, Maxwell's equations in electrodynamics, which you studied quite rigorously last semester. So these are things that you cannot avoid in whatever area you go. So some basic physical concepts will be needed. And the third broad area will be physical systems. I mean, with the idea of these concepts and mathematical methods, you shall then take up various physical systems like fluid systems, nuclear physics, projectile motion, planetary motion, gravity problems, that is, quantum mechanics. So all sorts of things. These are various areas where you will apply these physics concepts and the mathematical methods. With an understanding of all that thereafter, you shall develop codes, programs, and try to solve problems in these physical systems by coding. See, at school, you studied physics quite seriously, and there you were required to solve problems by pen paper method, using a calculator, working out problems, getting a numerical value. This is nearly that, except that occasionally you will have to, not just occasionally, quite often you will have to do the same thing, solve problems by hand. But occasionally in these problems, there can arise situations where you will not be able to solve a particular problem by hand. In that case, you will have to make use of programming methods, programming techniques to solve problems. So that is the broad kind of purpose of this course, to help you develop coding techniques, to make you learn coding techniques that can be applied to solve physical problems. And hopefully these things could also be applied to various other areas of physics as well. I mean, various other areas of physics or any other system. So fundamentally, it is just making use of coding to solve problems in physics. That is the basic purpose of this course. And as I said, there will be three broad areas. One will be mathematical methods. After all, if you have to code something, you need an equation. And the equation conveys a message about the physical system. For instance, Maxwell's equations, they contain a message, right, about the electric and the magnetic fields. I'm referring to Maxwell's equations because only very recently, barely 2 months ago, not even 2 months ago, you finished studying your course of electromagnetic theory. And so mathematical systems, mathematical methods, physical concepts, physical systems. So these are the three broad areas that we will take up one after the other. So that is about the what of the course. So what is the thing that you want to do in this course? Okay. Now let us take up the question of how we shall go about this whole business. Let us now try to see, or try to have an understanding of it. First of all, I mentioned to you that you shall have to do some coding, writing program. I make no restriction on your preferred choice of language. Be very clear about that. So people keep asking me, so what language we should use? I said, that is entirely your choice. To me, the coding part is secondary. To me, the important part is the physics part. Physics is independent of the coding. The math is independent of the coding. You can use MATLAB, you can use C or Python, whatever is your preferred language you use. So for that, so as far as coding is concerned, the algorithm is more important to me than the language, particular language in which you set down the algorithm. For instance, physics can be learned through the means of various languages, English, French, German. So many of the important researchers of physics, scientists of physics, they came from different countries. So the physics is independent of the language, and so coding is also dependent on some kind of language, but the language is not the subject. The language is just a means of understanding or analyzing the subject. So coding language, I make no restriction. So whatever language you are comfortable in, you write your programs in that language codes. Or okay, so that is the first thing. Now let us see. This is a 4.5 credit course. It has got 2 75-minute lecture sessions every week. Like today we have one first thing in the morning at 8:30, and then I think on Friday at 12 o'clock. Yesterday I sent all of you an email stating all these things. I made a slight error because I copy pasted from an old mail of mine, 2019. But this is a batch of 2020. So you're all in your fourth semester now, and you haven't set foot in the campus, which is a little unfortunate. Yeah. So this is a 4.5 credit course. You have 2 75-minute lecture sessions. Consult the timetable to confirm when your lectures are going to be. As I said, and the course will be conducted online. That will impose its own set of restrictions, also limitations, which is, as I said, unfortunate. This course could have been done in a more exciting fashion if we had met in person. Or, well, that's not to be, for the time being at least. So we are to meet in these 2 online sessions every week, and apart from that, we also have a lab. The laboratory session, as best as I can recall from the timetable, will be on Mondays in the afternoon from 2 to 5, 3-hour lab. I don't think we need to take up a full 3-hour session for that. So the theory courses, the theory classes will be conducted in this fashion only. That we will meet and I will discuss ideas. You will listen to me. The class, the session will be recorded, and later the recording will be sent to you, uploaded in a Google Classroom, and you will be given access to the Google Classroom. As of now, the batch has not been finalized. Therefore, I'm awaiting the finalization of this batch. I expect it to be done by the next week, and once the final batch list comes to me, I will admit all of you to a Google Classroom where all your course material will be kept. You will have the notes of these lectures, as those who attended my electromagnetic theory classes will remember. That is my usual method. You will have the notes of these lectures. You will have the recordings of these lectures. In addition, although we do not have any tutorial session, but I shall give you some problem sheets to work on. I do not expect you to face too much of a challenge solving those problem sheets. Occasionally, I may discuss 1 or 2 problems, but they are quite simple. They shouldn't be too difficult. At least I taught this course twice before. Nobody faced too much of a problem solving those problem sheets. So occasionally I will give you some problem sheets to work on that you can do. So that's roughly about the theory aspect of the course. So you'll get your books, notes, lecture recordings, all these things in the Google Classroom. The lectures are going to be held in the mode that we are going through right now. And now let us come to the laboratory part of it. Be a little attentive on this aspect of the course, the laboratory part. The laboratories, this week we are not to have any lab. I think it will start from next week. Let's see how it goes about. So what my usual practice is that for every week, just like last semester, every tutorial session you had a new problem sheet. So every week I will give you some laboratory problems to work on. So the laboratory sessions will be more like a tutorial session because we are conducting it online. I mean, lab means hands-on. Unfortunately, you can't have a serious lab online. But anyway, yours is a computational course. So here lab means doing things on your computer, on your laptop. So I believe all of you have your laptop. So be a little attentive about what I'm going to say right now, what I'm about to say. So in the lab, you are to form groups of two. So let us say that this class of yours, this class size will be about 70 strong, approximately in round figures, 70 strong. So I would advise all of you to decide on your laboratory partner. So two of you will form a group. I hope you're understanding what I'm saying. Two of you will form a group, and uh, in the lab session, all of you are supposed to be present. Attendance in the laboratory is compulsory, and it is not very difficult to check attendance because as soon as I start the recording, Google Meet will give me a full list of the people who attended the lab. So attendance is compulsory. The way we shall go about in the lab is the following. I will supply a laboratory, a set of coding problems to work on in the laboratory. At the start, every day, the lab session, I shall discuss the nature of the problem. I shall discuss the way you should be able to find the solution of the problem. With the help of the theory notes or whatever, I shall discuss that. And then you try to understand the problem. The laboratory session will be interactive. If you have doubts or any questions to ask, you are free to do so. And then after that, if you are satisfied that if you have understood everything about the problem, you can start working on the problem. That is to say, start developing a code. I mean, since you'll be doing it at home, on your laptop, of course, at home. Had you been in the campus, we have a very well-equipped computational science laboratory with powerful computers, and you could have been sitting in the lab and I would have supervised the work with the help of an assistant, a tutor, and he could have gone about the coding work for 3 hours in the lab itself, but that is not happening this time at least. So you shall have to do the work at home. Although officially the lab session has got 3 hours, I don't think it is necessary for everybody to sit through 3 hours. Once you have understood the nature of the lab problem, you can log out and continue the work at home. If you have any doubts or anything, you can immediately send me an email or whatever. You can also discuss the matter in the lab itself. Lab sessions are interactive sessions. And then a week later, you are supposed to submit a report on the work that you have done for that particular lab session. So typically, the number of problems that you are to solve in a particular lab range from 3 to 4 at most. At most 3 to 4 problems you'll be given to work on in a lab session. And so basically the week after you're supposed to submit a report on the work that you have done. The report will carry the name of both the partners, so with their roll numbers and everything. And I will evaluate that report. I'll tell you about the evaluation policy and everything soon, but that's the way you go about it. So I hope you have understood this point clearly. In the lab sessions, I will supply you problem sheets. We will discuss during the lab session how to solve those problems. Attendance in the laboratory is compulsory. I'll keep track of who is attending the lab session and not. And if you're not attending the laboratory, later you shall have to offer me some explanation as to why not, why you were not able to come to the lab. And once you have understood the nature of the problem you have decided, then you and your partner, both of you, I mean, you have to form groups of two. So that's why I'm advising you right away, you identify who the partners are going to be. And then after that, a week later, I will set up a Google assignment link in the Google Classroom. A week later, you are supposed to submit a report in that, and that report will be evaluated. So I hope you have understood this thing. And meanwhile, through the week, if you have any issues or anything, you're welcome to consult me on these particular problems. But I don't think people have any problem. I mean, that's going by my experience of the previous years. Everybody does well in the lab solving the lab problems. Anyway, you're free to have discussions among yourselves. I'm making no restriction on that. You're free to discuss with your friends. For that matter, you are even free to discuss with your seniors who have taken these courses. So the third year batch and the fourth year batch both were taught by me. So you can seek their help also in trying to understand the subject. As I said, learning the subject is more important. So I'm making no restriction as to how you go about your business. So that is about the lab aspect of the course. So I explained to you what the theory aspect of the course is going to be like and what the lab aspect of the course is going to be like. And I also told you prior to that what the content of the course, the basic objective and the course content are going to be, and then how the theory sessions are going to be conducted and how the lab sessions are going to be conducted. Now let us come to the question of evaluation and grading. Okay, so be very careful on this particular point. This is a 4.5 credit course. 3 credits are earmarked for the theory sessions and half a credit, sorry, 1.5 credit, 1.5 credits for the laboratory. So that's roughly 1/3 weightage is on the lab. That's why it is important that because computational physics, this is not theoretical physics. Theoretical physics is where you sit in your room, solve a particular problem by the pen paper method. But computational physics, you have to work on the computer, develop a code, solve a problem using the code. So that's why the lab session is important, and I insist 100% attendance for all of you in the lab. If you are not able to attend the lab or if you are unable to attend the class for any reason, you inform me beforehand, that is fine. I mean, I have no issues, but I'll just keep a record that you are unable to attend the class for this or that stated reason. Of course, the reason has to be a valid reason. Health issues, of course, are very serious valid reasons. So that's why it is important that, as I say, the lab sessions are very important. 1/3 of the weightage is on the lab. So as a result, you will be evaluated at the end of the semester, you'll be evaluated out of 100 marks, 100%. Out of that, roughly 1/3, 1/3 would be 33 out of 100%, but in round figures, I'm making it 30. You will have a 30 mark weightage, 30% weightage on the lab side of things, and 70% weightage on the theory side of things. There will be online examinations, I believe, in this semester, two certainly, one mid-semester examination and one end-semester examination. So let us look at or carefully understand the theory component of the evaluation. So there will be two online examinations, a mid-semester and an end-semester examination. And since the exams are online, the questions will be objective, like just in the same way your electromagnetic theory exam was like. You will have objective questions where you shall have to supply a numerical value for an answer with units or unit vector or sign or whatever. You are familiar with our method. I mean, in the last semester, you've gone through all of this. So the 70% weightage will be for the theory part, and the evaluation strategy or the examination pattern will be like what it was in electromagnetic theory. Objective question where you don't have to write too many things, you just have to supply a final answer. That's one aspect of the theory part of it. Now, this 70 marks will be distributed over 2 exams. So as of now, I can't tell you what the distribution could be like. It could be 30, 40 or 25, 45, something like that. Most likely 30, 40, very likely 30, 40. But as I said, I can't confirm anything right now. Mid-semester 30 and end semester 40, something of that order, near abouts. And the end semester syllabus will be cumulative, meaning that everything that you have studied through the semester. So you can't afford to ignore things that you studied early on in the end semester examination. So that is the theory evaluation part. Now let us look at the lab evaluation part. As I said, you have to submit a report within a deadline. The deadline should be respected, otherwise you lose marks. Now, each lab report, try to follow this point very carefully. Each lab report will be evaluated for 5 marks. 5 marks, right? So let us say typically in a semester there will be 12 lab sessions, roughly 12. So for each lab session, you will submit a report. So 12 into 5, you will have a total of 60 marks. And the report will be evaluated in the same manner for both partners. Both partners. Incidentally, I will later tell you, give you some sample reports from your senior batches to understand how you should prepare a report. And just as an aside point, I would prefer, follow carefully, I would prefer, although I'm not making it compulsory, that you prepare the report using the LaTeX software. LaTeX. LaTeX is important because now onwards you'll have to type a lot of mathematical expressions and stuff like that. And it is best done through LaTeX. You can submit it as a Word document. The report, final output of the report will be in the PDF format, by the way. You have to submit a PDF file, nothing else. So a PDF file you'll have to submit, ready to print like that. And I would prefer, although I'm not making it compulsory, that you use the LaTeX software to prepare your report. See, I'm not making it compulsory, but in the future, 1 year from now, when you do modeling and simulation and all those things, Professor Mukesh Tiwari will be teaching those subjects, and he will insist that you submit everything in LaTeX. So it's a very useful software for you to learn, particularly when it comes to preparing scientific documents. So I think it'll you take the trouble of learning it. But as I'm saying, I'm not making it compulsory for you, but it'll give you value. It'll add value addition to your CV. Learning LaTeX. It's a very handy software, particularly for scientific documentation or mathematical documentation. So I would prefer that you prepare your report in the LaTeX format, prepare a final output PDF file. I will evaluate that PDF file for both partners in the group out of 5 marks. Typically, average performance gets around 2.5 to 3. Very poor performance. If you consistently keep overshooting deadline, you will get no marks. And if you keep delaying, the total marks out of which you'll be evaluated will be reduced. So if you delay by 1 week or a few days, 2 or 3 days, you'll be evaluated not out of 5 marks, you'll be evaluated out of 4 marks. So like that. If you keep delaying even more, out of 3. After that, I'll award 0 for that. I mean, I can't keep waiting forever for you to submit your report. So best that you submit your report within a deadline. The deadlines are quite generous in the sense that you'll be given something like 7 days, or in the early stages, you'll be given more days because you need to familiarize yourself with the report preparing procedure. But in the later stages, students are perfectly capable of submitting the report within a week. Maybe in the early stages, I'll give you 10 days or maybe even 2 weeks or something like that. So these reports will be evaluated out of 5 marks. So suppose I'm just giving an example. You have got 12 reports. You submitted 12 reports in the semester. And so for the 12 reports, you have got 12 into 5, 60 marks. So these 60 marks will be reduced to 30 because after all, the full lab weightage in your 100% score will be 30%. So whatever total marks in the lab report that you have, that will be scaled down out of 30, and those 30 will be added to your theory marks. However, there is also something else. The theory performance is important for me to test your basic concepts. So I also put a weightage from the theory performance on the lab component. So out of the 30 marks, a small weightage, not small, some weightage will come from your theory performance. So suppose you have got two partners who are working on the same lab report. Lab-wise, they are the same, but the difference between the two of them will be understood through the difference in their theory performance. So that's why I want to keep some weightage for the theory part on the lab report as well. So I hope you're quite clear on that. 70 marks for theory, two examinations, distribution of marks, 30, 40, quite likely, but need not be so. End semester examination, cumulative full syllabus. Laboratory weightage, 30% out of 100%. These 30% will come from your lab reports. Each lab report will be evaluated out of 5 marks. Suppose there are 12 lab reports, you'll have 60 marks over there. Or 10 lab reports, you'll have 50 marks over there. If it's a total 60 mark lab score, then that will be reduced to half to make it 30. If it's a 50 mark lab score, that will be reduced to 60%. 60% of 50 is 30, so like that. And over this thing, I'll put a weightage from your theory performance. Usually people do well, both in the lab and the theory, so I do not expect you to have too many problems, too much trouble in getting a good score. So I hope you have understood the way your evaluation will be done throughout the semester. I've discussed with you the study method. The theory part will be just like what is going on today. The lab sessions, as we begin the lab, slowly and slowly you will understand. Within 2 or 3 weeks, you'll understand how we go about our lab work. So that should not be too difficult for you to appreciate or grasp soon enough. Next week we have a lab. Okay, so I told you about the theory part of the course, the lab work, the contents of the course, and the evaluation. Now the grading. Now the grading can be absolute, the grading can be relative. I really can't say anything right now. It will all depend on the overall performance of the batch. So for that, we shall have to await the end of the semester. However, there are two things that I impose in an absolute sense. What are the two things? That out of 100, to get a double A, you have to score 90. Be clear on that particular point. You have to score 90 out of 100 to get a double A in an absolute sense. If nobody gets 90, let's say that the class performance has not been good overall, relatively speaking, nobody has got 90 out of 100, in which case nobody will get a double A grade. So that's one thing. So regardless of whatever be the grading methodology, absolute or relative or whatever, unless you get 90 out of 100 in a real sense, then nobody gets, you do not get a double A grade. That's there. And similarly, out of 100, you will have to get 30 to pass in an absolute sense. So be clear on that particular point as well. However, for the computational physics class of the computational science batch, my experience is that passing is not an issue. You are supposed to be good students. So let us not worry about the lower half, that how you to pass. That usually doesn't, that problem you never, to my experience, has not arisen so far. So I shouldn't worry too much about the low end, that is to say, getting the pass mark. But if I were you, I'd rather be careful about the high end. That is to say, to get a double A grade, you have to get 90 out of 100, which shouldn't be too difficult. Students get it. Students get it. So if you're attentive and focused on the course and the way it goes about, it shouldn't be too difficult after all. And it should be your aim to get good score in computational science, because 2 years or 3 years from now, typically computational science students, many of them go for higher studies abroad. And so if you go for higher studies to American universities, good grades are important. A wide range of subjects to show in your transcript is also an important aspect. And if you have these things, it also becomes easier for us to give strong recommendation letters. So That's one aspect. So the knowledge that you will acquire through your computational science honors curriculum will have multiple positive benefits, effects for you, multiple benefits for you. You can go for higher studies. Many students have gone on to study computational science courses at the master's level from GICT only. I know that. Or with all the extra knowledge that you acquire in coding and solving physical problems, these can be useful in the industrial domain as well, in research groups of companies or wherever. So it's a brave decision that you have taken, and so you should also try to ensure that you are amply and generously rewarded by this brave decision of yours. That is to say, you do well in all the four subjects, core subjects that you take up. If you do well, that will improve your overall grade, it will enhance the value of your CV, it will open various career opportunities for you. So that is why you have taken up this extra load. You're doing some extra work. So anyway, so that is the broad theme of this course. I've spent about half an hour discussing all that, so I hope you have understood it. I will, of course, supply you the recording later of all this. And so with that discussion, I don't think I have much else to talk about. I hope you have understood. If you have any questions or anything, you can ask me at the end of the class. My usual method is that unless there's some serious problem with the audio quality or the presentation or anything, I would prefer that you remain muted, and then later at the end of the class bring up an issue, be it a technical issue regarding the physics aspect that we are about to begin now, or non-technical issues pertaining to the course. Non-technical issues, the sort of thing that I have been discussing so far. We spent about 35 minutes talking about all that. Anyway, so with that, I shall now begin the discussion of the course, the first part. I hope all of you can see the presentation. Can you just confirm that you can see the presentation clearly once more before I start? One of you please confirm to me. Hello?
Yes, sir.
Yes, sir.
Okay, okay. Thank you very much. Mute your mic, and we shall now begin the technical discussion. So as I told you that this course is divided into the study material, the content of this course is divided into three broad areas: mathematical methods, physical concepts, and physical systems. So we begin with physical concepts first. Once we have an understanding of the concepts, then we can go into the math aspect of it. And then with the help of these two tools, we can attack some physical problems later. That is for later. But the kind of things that I'm about to take up will have validity in all areas of physics. So the first technical topic that I would like to discuss today pertains to dimensions, scales, and physical constants. Let us see. Now, in your school knowledge of physics, you know that there are three basic dimensions of mechanics: mass, length, and time. These are the three mechanical dimensions of mechanics, mind you. If you bring in electricity and magnetism again into all of this, then opinion is divided as to what should be. Some people say charge, some people say no, current. I mean, Resnick and Halliday's book, I think, gives charge, but some other books give current. Anyway, we are not getting into that. We're just considering the three mechanical dimensions: mass, length, and time. Now, first thing that we have to do, when I say dimension, I mean the physical mechanical dimension. I'm not referring to the other meaning of the word dimension, such as one dimension, two dimension, three dimension, one dimension as in the x-axis, two dimensions as in the xy axis, three dimensions as in the xyz axis. So I'm not referring to that. I'm talking about the three mechanical dimensions of mass, length, and time. Our purpose will be to see, I mean, the reason why I want to have this basic discussion is to see, I mean, are they really very serious, valid dimensions? We may think that they are important, but are they really are? We shall take up this question in the long run. through this discussion. So first, let us try to see what these dimensions tell you about nature, or how you are able to understand or access nature with the help of these three dimensions. Let us try to see. I've written something over here. In these dimensions, the scales that we can appreciate by our senses are scale. Scale meaning this on this scale, this is what it is. These are the orders of magnitude estimates in the SI system. Let us try to understand that. First, let us consider mass. By our senses, meaning, let's say that you are living 1000 years ago, when there was not much technology available, not much precision measurement available. You have to understand nature by your sensory powers, such as your eye, your muscle power, your ears, all these things. Just by your senses, how much of nature can you appreciate? The scale of nature that you can appreciate. M, as in the mass dimension, how much can you appreciate? How much mass can you appreciate uh, the scale of it? Let me try to explain to you. Can you lift a tree, large banyan tree? Very likely not. Can you lift a train? Very likely not. No, I don't think so. Not even very likely not. Can you lift a mountain, a hill? Of course not. So, as far as you are concerned, a train is as heavy as a tree or as a mountain, because you can't move any one of those three things. Nature has not designed you to push around such large, massive objects. However, can you appreciate the difference between the mass of a, let's say, a simple notebook? I expect that you are having a notebook in front of you right now. Incidentally, yesterday in the mail that I wrote to you, I asked you to maintain a notebook. You should jot down these points, later go through them for clarity of understanding. You should be able to understand the difference between the masses of a notebook, let us say, and a piece of furniture. Let us say the chair on which you're sitting right now. If I ask you, if I blindfold you, wrap a cloth, black cloth over your eyes, and I ask you, here, hold this notebook in one hand, you can't see the notebook, and you hold this chair in the other hand. And I ask you now, without looking at either of the two, can you distinguish the two of them? You'll say, yes, of course I can, because the chair, by your experience, is heavier than a notebook. You're able to appreciate the difference of the mass of a notebook and a chair, or maybe a heavy piece of furniture, or maybe a heavy suitcase, and a very light object like a pen or a utensil or whatever. Nature has designed you to appreciate the difference of masses on this scale. What is the largest mass that human beings are capable of moving so far? What's the world record? The world record for weightlifting, heavy weight category, is somewhere below 500 kgs. It's not 500 kgs. Of course, a tree is much heavier than that. A train or a lorry is much heavier than that. A mountain is certainly much heavier than that. So you'll not be able to move any one of those things. So as far as you're concerned, blindfolded, if you might be, you will not be able to distinguish the tell the difference between the mass of a lorry or a train, something like that. So the heaviest weight that you can lift and tell the difference between it and something else is of the order of 10 raised to 2 kgs. 500 kgs is the world record. So even less than 500 kgs is the world record for heavyweight category weightlifting. So 500 will be 5 into 10 raised to 2 kgs. Right, so I'm dropping the 5, and just in an order of magnitude sense, you'll have 10 raised to 2 kg. Of course, The person who lifted that weight is a very strong person. Not all of us are very, very strong. So at most, you'd be able to lift something close to 100 kg, perhaps not even that. So 10 raised to 2 kg is our normal experience of moving a heavyweight object around. What about the other end, the lower end? Um, can you tell the difference between uh, bacteria and an electron? I do not think so. Although you know that a bacteria will be much heavier than an electron. But you are not designed by nature to understand the difference of the mass of a bacteria and an electron. What's the lowest mass that you can kind of correctly make a measure of by the application of your senses? Once again, I'm telling you, just by the holding the object in your hand, trying to lift it, holding try balance it on your fingertips, something like that. If you're a goldsmith, let's say, goldsmiths work with very small amount of gold of the order of one or two, a few grams that they want to put in ornaments. So goldsmiths have a fine sense of small weights, but it will not be less, significantly less than 1 gram. 1 gram is how much? 10 raised to minus 3 kg, right? Maybe even a fraction of that at most. Nobody is designed to appreciate the difference between the mass of a microbe of the order of 10 raised to minus 6, no, sorry, 10 raised to minus 6 meter, sorry, a bacteria, a microbe, let's say a bacteria, and a nanoparticle or an electron or something like that. Nature has not designed you through your senses to probe uh, scales of matter, scales of masses in the very small domain. And similarly, nature has not designed you to probe scales of mass on very large scales. By the application of your senses, you have been designed by nature to understand the difference of masses going from 10 raised to minus 3 kg, which is about 1 gram, to about 100 kilogram. So 10 raised to minus 3 kg to 10 raised to 2 kgs. So that is the scale of nature in the mass dimension that you are able to access or appreciate. Okay, now let us try to understand the length scale. Are you capable of seeing an atom? Of course not. You are not even capable of seeing a bacteria. You're not even capable of seeing the virus that is entering your nostrils or your mouth every minute. If you were capable of seeing virus, then avoiding the coronavirus could have been so much easier, right? They are very small objects. An electron or an atom is even smaller because ultimately bacteria and viruses are made up of atoms, charged particles, and all these things. They are much larger than an atom, but you can't. Microbes, things that occur on this length scale of 10 raised to minus 6 meter, micro 10 raised to minus 6, right? So you're not capable of seeing that. What is the, just by looking at something, how much of smallness can you appreciate just by looking at it? Length you can only, if you did not have, as I said, you're living 1,000 or 2,000 years ago when people did not have much, did not have a very clear idea of measurements, physical measurements. How much of a small length could they have been able to appreciate with the use of their eyes? Remember, in those days, there were not even spectacles or glasses. So if you had some problem with your sight, a problem that you gradually develop with advancing years, you will not be able to see much of anything in your later life. So 10 raised to, just think of a simple ruler scale that you use, a 1 foot scale that you use. If you look at it carefully, you will see that the least count of the scale, I'm using the word least count now, the least count of the scale is about a millimeter, right? Two grooves on that scale, two adjacent grooves, mark out a separation distance of 1 millimeter. So you are not really able to see anything much smaller than that. Maybe a fraction of a millimeter, 1/10 of a millimeter maximum. You'd be able to distinguish the little gap between two grooves, and that distance is 1 millimeter. So maybe a fraction of a millimeter is what you should be able to, if you have a very good eyesight, that is. Not much less than, nothing much less than that. So a millimeter is 10 raised to minus 3 meter. And here, if I say that at best you'd be able to go down to distinguishing the length of a fraction of a millimeter, 1/10 of a millimeter, let's say that's the smallest fraction that you may be able to just make out. So that will be just something like 10 raised to minus 4 meter. That's about the smallest length scale that you can appreciate with your eyes. You'll not be able to make out. As far as you're concerned, there is nothing smaller than that that you can make out with your eyes. You can't make out the difference between the size of a virus and the size of a hydrogen atom. Nature has not gifted you with that machinery. And then let's go to the other end. What's about the largest length scale that you can make out with the help of your unaided eye? If you stand on top of a building and have a clear view of the horizon, particularly those who stay away from congested cities, you'll see a clear view of the horizon. It's difficult, really. If you stay in the southern suburbs of Gandhinagar city, some of you may have your homes in Gandhinagar or Ahmedabad. If you stay in the southern suburbs of Gandhinagar city, if you stand on the terrace of a newly constructed high-rise flat building, you'll be able to get a view of Ahmedabad, on good view of Ahmedabad on a clear day. So that's something like 30 kilometers away at most. So if something is 50 kilometers away, probably you'll not be able to make out. Or if something is closer, something is farther, these things you're not really able to make out very clearly. They could be 20 kilometers away, 30 kilometers away, 50 kilometers away. The higher you go up, you'll be able to see more far out, but you'll not be able to make a sense of the scale of distance. This becomes even more stark when you look out at the night sky on a clear night. This is late winter now. Sankranti is gone, and so now the night skies the days are slowly getting warmer, and the night skies are getting clearer. You don't have too much of a fog. So if you look out in the night sky, you'll be able to see the stars, and occasionally across the background of the stars. Note my use of the word the background of the stars. You'll be able to see a planet or two before the setting of the sun. You could make out the planet Venus, which is popularly known as the evening star. Or later in the evening, you should be able to make out the planets Jupiter, or even Saturn or Mars. These are planets that were well known to humankind without the use of telescopes, right? Now, if you look out in the night sky and see the planet Jupiter, it'll just be like one of the stars. But we know from our basic knowledge of astronomy that the stars are much, much farther away from us than the planets are. The planets are on the distance of the order of a few 100 million kilometers. Right, a few 100 million kilometers. So maybe some crore kilometers. But stars are light years away. The nearest star is 4 light years away. It's so far away. Even the nearest star is so far away. Light that travels at an enormous speed of 3 lakh kilometers every second. That light will take 4 years to arrive at our eyes, having started out from that star. But if you look out into the night sky, the planets and the stars could be like they look like that they are at the same on the same dark background. But the reality is that stars are much farther away from us than the planets. But you can't really, with your unaided eye or without any instrument, make sense of that great distance between the two things. At most, standing on a hilltop looking far out into the horizon, you can make things out a few kilometers away. So a kilometer is about 10 raised to 3 meter. So I say a few kilometers away, a maximum 10 kilometers away at, let's say, 10 or 20 or 30. So that's something like 10 raised to 4 meter. 10 raised to 3 meter is a kilometer. And so something of the order of magnitude of 10 kilometers on that scale, you'll be able to. So nature has designed you to appreciate the world or the world all around you on this scale. If you notice the scale over which I'm running the mouse cursor, the movement. Now let us consider time. As I said, you do not have the advantage of any apparatus, your watch or phone or atomic clock, nothing. You do not have the advantage of any apparatus. What is the time scale that nature has designed you to appreciate? Let us see. A very standard, by the way, if you consider your body, just think of your body. If you consider your body is actually a clock in many ways. And it's a very strange kind of a clock because any clock that you have operates on only one particular time scale. Try to follow that point I'm making. Any clock that you have operates on one particular time scale. Like, let's say, your wristwatch. It is operating on a time scale. What's the minimum time scale? Least count, so to speak. Note my use of the word least count, and I shall use this word again and again later also. The least count. Least count is very important. Why is it important? Because it helps us understand the limitations of our measurements. But then why are we interested in knowing the limitations of our measurement? Very simple thing. We have to make measurements because we are doing physics. It's an exact science. It has to give you numbers. We are not doing philosophy or poetry. When I say blue sky as a poet, it's all very nice to say a blue sky. But what is blue? If somebody is blind or somebody is colorblind, let's say, what is blue to that person? How will you make that person understand what is blue sky? There is a way to make that person at least have an appreciation of what blue sky is, a sense. I wouldn't say appreciation, a sense of what blue sky is. When you say blue means 400 nanometer wavelength of light, that is an exactly measurable quantity. Someone who is colorblind or somebody who can't see, unfortunately, if somebody can't see, you can still make that person have a sense of the word blue or have a sense of the word red. What is red? You will say 700 nanometer or 7,000 angstrom, or blue is 4,000 angstrom or 400 nanometer. So that is why measurements are important in physics. Otherwise, it's just so much philosophy or talk. You have to have some appreciation of numbers, and to get those numbers, you have to make measurements of nature. And why nature? Because we are doing physics. Once again, I stress this thing. We are doing physics. We are not doing mathematics. Although I've written so many numbers and equations and all those things, and we'll keep doing that again and again. But we are not mathematicians. We are physicists. Mathematicians use equations for a philosophical purpose, for an aesthetic purpose. We use mathematics as a way of understanding, of getting a sense of nature. But to us, nature is the first thing. And therefore, to be able to understand nature, we have to make measurements of nature, natural phenomena. And then those measurements are cast in terms of numbers and units. And as soon as we talk about numbers and units, we will have to be concerned about least count. So what is the limitation of the least count of our apparatus? With your eye, can you appreciate light years or the size of galaxies? Answer is no. With your eyes, can you appreciate the size of an atom or a bacteria? The answer is no. So your eye has a least count, right? With your strength, bodily strength, can you appreciate the mass of a mountain or the mass of the moon, the difference of the two? No. And so with your bodily strength, can you appreciate the mass of an electron and the mass of a proton, although they are 1,000, 2,000 times, nearly 2,000 times different from each other in terms of mass scale? So no. So your body has a least count. Your body is also a measuring, can be used as a measuring apparatus. And nature has designed you to appreciate all natural phenomena within a certain scale. And so your body also has a least count. However, your body is a very strange machinery. You consider a watch, as I was telling you, you consider a watch. What is the least count of the watch that you can have? A watch operates at most on a second. Your watch doesn't certainly operate on a scale of a nanosecond or a picosecond. Operates only on a second, right? And your watch operates, I mean, there are three hands in your watch: the minute hand, the second hand, and the hour hand. So your watch is capable of measuring time on three different scales. So that's the way you have designed your watch. Similarly, your body operates on various time scales. Just consider your heartbeat with which your pulse is connected. If you fall ill, the doctor will measure your pulse. That is operating on a time scale of 1 second. Every second, there is a throb in your vein on the wrist, which the doctor will measure if you fall ill, right? He will count your pulse. So that's on a time scale of a second. The blink of an eye is of the fraction of a second. Note that point. That's far more quicker time scale than the watch which you see, which measures time at best on the second of a, on the scale of a second, right? The blink of an eye or sneezing or those things operate on a time scale of the fraction of a second. Then your body also has a 24-hour clock. Just like your heartbeat or your pulse operates on a second time scale, your body, entire body operates on a 24-hour time scale. What is that? I mean, how do you appreciate that? Just travel to America or buy a jet plane, or you come back from America. If you have done so, you feel the phenomenon of jet lag. What is jet lag? Your body has been shifted by a time scale of 12 hours, but your body is designed by nature to operate on the time scale of the cycle of the sun. The sun rises, your body becomes alert. The sun sets, your body slowly goes to sleep. Nature has not designed us to be nocturnal animals. We are, I mean, there are other animals which are nocturnal, but we human beings belong to the family of apes. Apes are not nocturnal animals. I mean, if you had stayed on in the campus, you'll find, I mean, by the way, the DICT campus has got a whole lot of monkeys all over the place. You'll see them in the daytime, you will not see them in the nighttime. So at nighttime, they go to sleep. That's the way their body cycle has been designed by nature. And we belong to the family of apes, human beings. So our body is also following the same cycle, except that with the help of technology, we have created light and music and all those things, and you can stay up all through the night. But if you did not have all these facilities, technological facilities, then you would have fallen asleep soon enough. So that is the thing that you have. Your body is operating on a time scale, on different time scales. Now, what's the lowest time scale? If you want to measure some phenomenon using your body clock, sub-body clock, at most you'll be able to measure something on the scale of a fraction of a second. You say, oh, well, I saw that thing happen in the blink of an eye. A blink of an eye is the fraction of a second. So 10 raised to minus 1 second at most. Your pulse beat is about on the scale of 1 second. So you're not designed by nature to see the transition of an electron from one Bohr orbit to another Bohr orbit, which happens on the time scale of a nanosecond or a picosecond, right? Nature has not designed you to appreciate phenomena happening on such a small time scale. Now go to the other end. Has nature designed you to appreciate phenomena happening on, let us say, geological time scales, which happens on a scale of millions of years? Of course not. Has nature designed you to appreciate phenomena that will happen on a time scale of, let us say, 100 years or 1,000 years? Of course not. At most, you'd be able to understand the difference. Let's say you plant a tree, a small plant, right, in your flower pot. Of course, every instant of time, the plant is growing. You water it, place it under the sun. But if you keep looking at it, you'll not be able to see the plant grow in front of your eyes. But on the time scale of a month or 2 months, you'll suddenly realize, hey, the plant has grown quite a lot. Or maybe you keep a pet or a child you see growing up, right? You'll suddenly say, if you see the child after 1 or 2 years, you'll say, hey, how much have you grown? How tall you have become? But even as the child is growing, you'll not be able to say that in this instant its height was, the child's height was this, and then in the next instant its height has become more. No, so those things are happening on so slow a time scale. So those are so slow a process on a much longer time scale that you'll not be able to appreciate immediate changes, right? So what's about, I mean, what is the time scale over which you are able to appreciate things happening on the time scale of happening or changes happening? That's on the time scale of with your body senses, that is. That's on the time scale of a few hours, right? An hour has got how many seconds? An hour has got 60 minutes, and a minute has got 60 seconds. So an hour has got 3,600 seconds. So that's something like 10 raised to 3 seconds. So maybe you can put, say, 10 raised to 4 seconds at most, right? 10 hours or something like that order. So 10 raised to 3 seconds, 10 raised to 4 seconds. So that's the time scale on which you will be able to appreciate things changing. So these are the scales. These are orders of magnitude estimates in the SI system. By the way, in our course, the usual system of unit that we shall work with is the SI system of unit, kilogram, meter, second. That is the thing. Okay, just want to tell you. I mean, later you shouldn't have any confusion. Now the question is that why have we been designed in this scale of nature, mass, length, and time? Nature has drilled us these scales. Just a while ago, I told you, we are apes. Every species on Earth is designed to live within a certain ecological niche, right? Like whales live in the water, oceans, monkeys live in the trees, birds fly in the air, other animals live on open grassland. So whatever, I mean, forests or whatever. So depending on the kind of ecological niche through which a species has evolved, nature has designed that members of that species to appreciate her. That is to say, nature on certain restricted scales. That is, and why is the scale restricted? This is a particularly important point. I'll give you another example. Every now and then, just a while ago, I gave you the example of light, 400 nanometer to, what did I say, 700 nanometer. Why are you able to, the last semester you studied electromagnetic waves, electromagnetic theory. Electromagnetic waves have a very high range, very long range, starting from microwave, radio wave, infrared, visible light, beyond visible light, you have ultraviolet, beyond ultraviolet, you have X-rays and gamma rays. You only see a small, your eyes are capable of seeing only a small portion of this electromagnetic spectrum. Why do you think that has happened? Is there anything else that you can see? Well, the answer is that, very simple answer. Nature did not design human beings. We human beings see the world in the so-called visible spectrum. There is nothing very special about this visible spectrum, visible part of the electromagnetic spectrum, going from 400 nanometer to 700 nanometer, except that the home star nearest to which our planet is, which is the sun, throws out light predominantly in this so-called visible spectrum. The sun is yellow in color. Blue is slightly to the left of yellow in the spectrum plot. Red is slightly to the right of yellow. Violet, indigo, blue, green, yellow, orange, red. Right? The sun is yellow in color. So most of the planet that we see is showered by this light, illuminated by radiation in this range. And nature, and since we are day-dwelling creatures, nature has designed this part of the visible spectrum drilled, hardwired. That is the thing. Hardwired this part of the visible spectrum in our eyes. Nature has not given us X-ray vision or infrared vision because nature has not designed us to be night-dwelling creatures. We just have to live in the day and see the world in sunlight. And the dominant part of sunlight comes from 400 nanometers to 700 nanometers. But some creatures actually see in infrared. I hope you are aware of that fact. Snakes, which hunt in the night, in the dark, they see things in infrared. These days you'll see so many thrillers and all those things where soldiers wear infrared goggles to see in the night. But that's technology. Nature has not given us infrared vision. In fact, there are other creatures also who don't even use light to see, so-called. Bats use sound to locate and see. Or inside the ocean, bats fly about in the dark, in the night. So in the night there is no light. So they see their world with the use of, so-called see their world in the use of, with the use of sound. Similarly, in the ocean, in the deep dark depths, whales echolocate, dolphins echolocate. So they see things, so-called see, quote unquote see, with the help of sound waves, not light waves. So you can see the scales in which we operate, nature has designed us to operate, are the outcome of the natural evolution through which we have gone for the requirement of our survival. Now let us understand the business. I mean, this discussion is important. Why am I discussing all these things? Because ultimately we shall have to appreciate that nature's own scale is far, far larger than this thing. And to understand physics, we shall be working with a wider range of problems, from the atomic domain to gravity and planetary dynamics and all these things. It is a marvelous matter that as human beings, we are an intelligent species. We have been able to appreciate natural phenomena. Note this point very carefully. We have been able to, as a species, we have been able to appreciate natural phenomena on scales which were intended to be forbidden to us by nature. Nature did not want us to see the atom. Nature did not design us to understand the scale of galaxies. And yet we have done that. So we have transcended barriers set upon us by nature. And that we have done with the use of our reason and intelligence. So that is the thing. Otherwise, just for our survival, for your survival, you do not need to worry about the atomic structure. For your bodily survival, you do not need to worry about the size of the Milky Way galaxy. So for our natural survival, to be able to live, this is the scale on which, I mean, appreciating nature on this scale is enough for us. 10 raised to minus 3 kg to 10 raised to 2 kg, 10 raised to minus 4 kg to 10 raised to 4, 10 raised to 1/10 of a second to 1,000 of a second. Now, what do I mean by survival? What is this thing? Let us see. Just it's a familiar formula. H is equal to half gt squared for you. We are all descended from apes. Apes were hunted down by predators, tigers, let us say, or lions, whatever, in the jungles, right? What is the reflex scale on which you operate? Reflex. On the time scale of a second. Just give you a simple example. If you're a fielder playing cricket, the game of cricket, to be able to take a catch in close quarter positions, let's say the slip position or the point position, you have to operate very quickly. But how quickly do you need to operate? Do you need to operate on the time scale of a picosecond or a microsecond? No. Just operating on the scale of a second will be enough to take a catch, a fraction of a second or a second or whatever. On that scale, if you operate, so we don't move around on time scales faster than that. We move around on time scales of a second. Anyway, so in the next class, because it's 9:45 now, I have spent enough time discussing the background of the course. I hope you have understood this thing. I'll stop the discussion here because time is up. In the next class, which is on Friday, we will continue this discussion. My point will be to make you appreciate that these scales that we see nature on, over which we appreciate nature, have been drilled into us, hardwired into us due to the imperatives of survival. Due to the imperatives of survival. We shall see about that soon enough. In the next class, we shall continue with this discussion. And then, of course, this last statement, we shall try to understand. Nature operates on vastly larger scales. And to be able to understand the physical universe, we need to understand those scales as well, transcending the limitations set upon us by nature. Anyway, I shall stop here. You can ask me questions now if you have any. Otherwise, we can stop for the day. Anybody has any question to ask? Nobody? If you do not have any question to ask, then you may please leave. I shall stop the recording. I will give you the recording and everything in due course. Please bear with me once the batch list is finalized. We shall meet on Friday. If you don't have questions to ask, you may please leave.